and they get transmitted over what is known as Gaussian noise channel, additive Gaussian noise channel, and the receiver gets the transmitted voltage plus the noise voltage, and the noise voltage uh, is assumed to be having Gaussian distribution, and the transmitted voltage is a constant. It is either a positive constant or a negative constant depending on whether bit 1 is sent or bit 0 is sent. Now, if you recall, in the beginning of this FDP, we had studied the topic of Bayesian theorem, right? And so that we studied in the context of coronavirus disease detection. We said that the model of the presence of the disease in the body versus the outcome of the test in the laboratory can be represented in this diagram. There are two possibilities, whether one has the disease or doesn't have the disease. There are two possible outcomes. The test outcome is positive or negative. But because there are these erroneous events, we have to apply Bayes' theorem whenever we observe a particular output in the world. Whenever we measure something, we have to go back, as we looked at here. Sort of, we have to kind of move in the opposite direction in this diagram and evaluate the relative likelihood of whether C is equal to 0 or C equal to 1 in the case when test outcome is negative. Or if test outcome is positive, we again do the same look back, or we go back and kind of evaluate the relative likelihood of C equal to 0 versus C equal to 1 in that case. And that rule by which we do this looking back mathematically is known as Bayes' rule. Bayes' rule says that probability of the cause, the ith cause given the jth evidence, this is the look back part, right? We have the evidence here, y of j. In the earlier diagrams, I was calling it t of 0, t of 1. I think test outcome is positive or negative. But in general, let us call them as variable y of j. So given y of j, we are looking back and evaluating the likelihood of individual causes, x of I, whether the disease is present or disease is absent. And that likelihood is called posterior, meaning what is the likelihood of the different causes post the measurement of the evidence. That's why it's called posterior. And that posterior is, according to the Bayes' theorem, is directly proportional to the prior, meaning what was the likelihood of the different causes before even you went and did the test, times the likelihood function. What is the likelihood of observing a particular test outcome given a particular cause, and then we divide it by the evidence. This division by evidence is sort of like normalization. And then basically we select that particular outcome for which the posterior is maximized, and that is what we did by this calculation, right? And we saw that when we did this calculation, probability of x equal to 0 given y equal to 1 is 84%, and probability of x equal to 1 given y equal to 1 is 16%. So we said that relatively the chances are still greater that the person doesn't have disease even when the test result came out positive. Now, in this is the exact same model that we are applying for BPSK demodulation. The two things that we are doing differently is, first of all, we are not bothered about this evaluating the probability of evidence. Why? Because once we observe a particular output at the BPSK receiver, that particular output remains the same for all the possible causes, whether the transmitted bit was 0 or 1. So when we are trying to do the relative likelihood ratio, the evidence, the term in the denominator is a constant and it cancels out. So we do not worry about evaluating evidence explicitly. That is what we did here as well. Remember this alpha term? See, this alpha term is remaining unchanged whether we are evaluating the likelihood of x equal to 1 or x equal to 0. So in the relative sense, when we are considering the ratio of likelihoods, remember we did that ratio of likelihood here, this ratio of likelihood, lambda. When we are doing that, this alpha, which is a constant, cancels out. And now we have to worry only about the numerator terms. Now in the numerator term, both the terms that are getting multiplied, the likelihood and the prior, they do depend on which x of I we are looking at. So they don't cancel out the way the evidence term got cancelled out when we took the ratio. But if we make additional assumption that the priors are all equal, probability of 0 is same as probability of 1, and that is equal to 0.5. Then again, when we take the ratio, because these two terms are equal, they cancel out. And that is why here we are left with only the likelihood terms. Probability of r given x equal to 1, probability of r given x equal to 0. That is exactly this term, probability of yj given xi. So you can see that this analysis that we did yesterday follows directly from Bayes' theorem, the probability evaluation according to the Bayes' rule. And surprisingly, that rule applies to our day-to-day lives. We did so many different examples where we are constantly, our brains are constantly evaluating the relative likelihood of different possible causes, sort of based on the evidence that we observe or we measure or we experience. And that same exact model applies to the binary symmetric channel, that same model applies to binary eraser channel, and that is how we can do the detection of noisy channel codes. Remember we yesterday looked at repetition coding, or we looked at single parity check code, or we even looked at the product code. In all of that, the fundamental problem is exactly the same, that the decoder of a forward error correction coding observes certain output coming out of a noisy channel, either a binary symmetric channel or binary eraser channel, and it has to look back. Okay, I'm getting some messages that somebody is unable to hear the audio. Is that still a concern?
No, we can hear you perfectly fine. Probably that's a local problem.
Okay. Okay, then I'll continue forward. I will ask a question. See, this time because I had some technical difficulty, I'm not able to actually directly see the messages. Somehow, this WebEx is not cooperating with me today. But
I will coordinate it for you. If there are questions, I can.
Okay, fine. So because I want to ask a question to the attendees, that
Sure.
in I have a different type of modulation scheme where x equal to 1 is still encoded at plus 1 voltage, but x equal to 0 is basically modulated by just switching off the transmitter, meaning that for x equal to 1, instead of transmitting -1, we transmit a 0 voltage. We don't transmit anything basically. But the noise remains exactly the same. In that case, without going through all the math that we just now did, what would be the decision boundary? That is my question to the audience. Did you understand my question? I'm considering a modulation scheme which is slightly different from BPSK. In BPSK, bit 1 and bit 0 are transmitted as plus 1 volt and -1 volt, or plus A and minus A in general, where A is some variable. There is another scheme which is called on-off keying or amplitude shift keying, where bit 1 is sent as plus A volt, but bit 0 now is sent by switching off the transmitter, meaning that it corresponds to 0 voltage. Assuming that the noise characteristics remain identical, then what would be the decision boundary? That is my question. Does anybody have any thought regarding that? Let me put it this way. The blue colored conditional PDF remains exactly the same for on-off keying. But because we are transmitting 0 volt instead of -1 volt for on-off keying, this red colored PDF, instead of being centered at -1, it comes and moves at r equal to 0, meaning that it is now centered at r equal to 0. Conceptually, that is the main change between BPSK and on-off keying. What would you say now, that how would the receiver decide when it observes a certain value of r at the output of the channel? Specifically, what should be the decision criteria? What should be the decision rule for on-off keying? Does anybody have any answer to that question?
So one answer is posted, which is R equal to 0.5.
That is the correct answer. So let me go back. Yeah, r is equal to 0.5, correct. So that is the right answer. And that answer actually comes directly from the observation that these two PDFs are symmetric. And therefore, their intersection, the point at which this lambda variable becomes exactly 1, which corresponds to the decision boundary, always lies halfway between the two transmitted symbols. And the middle point of 0 and 1 is 0.5. And so that is why the decision boundary becomes 0.5. The other way to think about this is that if we apply the minimum distance detection criterion, then again the midpoint is the boundary at which the minimum distance is flipped. If you are on this side of the midpoint, then the distance to that particular transmitted symbol is the smaller compared to the other one. Versus if you go on the other side, then your decision has to change because the minimum distance has changed in the same manner. So that is the fundamental observation, that the decision boundary for maximum likelihood detection. Remember, the key assumption we are making is that the maximum likelihood ML rule is optimal. What is the ML rule? It is the one that I have mentioned here, that x equal to 0 and x equal to 1 are transmitted with equal probability. That is the ML rule. So if this assumption is met of equiprobable symbol being transmitted, then we can apply ML rule, which is the optimal Bayesian detection under this assumption. And additionally, if the noise is Gaussian distributed with zero mean, then the decision boundary always lies halfway between the transmitted symbols, and it coincides with the decision boundary that we will get with the minimum distance detection rule, which is what we have looked at on this slide. Okay, we went over the probability of demodulated bit error, and we derived certain mathematical expression for analytically evaluating the probability of detection error. And yesterday we started looking at some constellation diagrams, both at the transmitter, which is the one shown on the left hand side here, as well as at the receiver, where we can also observe what happens to the transmitted symbols by the time they get to the receiver through this additive Gaussian noise channel. What this model allows us to appreciate is basically the main conceptual aspect of classical communication systems, classical digital communication systems. We are able to appreciate the decision boundary when we are transmitting +1 and -1. Essentially, our maximum likelihood Bayesian detector, assuming that x equal to 1 and x equal to 0 are equally likely, simplifies to minimum distance detection rule. And minimum distance detection rule, all that it does is whenever it receives a particular value of r, it measures the distance to the two possible transmitted symbols, in this case E1 and E2. And then it decides on that symbol for which these two different vectors, the one which is the smaller of the two. So in this case, because E1 is smaller than E2, we would decide in favor of this particular symbol being transmitted. And that allows us to say that the decision boundary is exactly halfway between the two transmitted symbols. So this diagrammatic representation of what is going on at the receiver is kind of somehow capturing the essence of the classical communication theory by leveraging upon the Bayesian probability, the Bayesian theorem. We also were able to theoretically evaluate the probability of error when the detector is this optimal Bayesian maximum likelihood detector. And we saw that that probability of error has this expression, Q function of A divided by sigma n. What is A? Remember, we said that A is square root of the transmitted energy per symbol. Over here, we defined the transmitted energy as A squared. A is voltage, and so when I square it, I get a quantity which is proportional to the energy. There is some proportionality constant, but that constant is omitted to simplify the mathematical representation. And that omission is not anywhere limiting, because that constant of proportionality is the same regardless of which symbol is being transmitted, and so it cancels out. So we can say that energy per transmitted symbol is A squared, basically the square of the distance of the constellation from the center of this chart, basically the origin. So A is square root of energy per symbol. Sigma n is square root of the noise power. Sigma n is the standard deviation, and that is capturing the noise power. This diagram again represents the BPSK transmission. So now instead of saying that the two symbols S0 and S1 are being transmitted at plus A and minus A volts, we'll say that they are transmitted with plus square root of energy per bit or energy per symbol and minus square root of EB. This is the transmitter side constellation diagram. At the receiver side, we get a diagram where there are conditional probability density functions superimposed. And then because 0, the voltage of 0 is the decision boundary, the probability of error when S0 is transmitted is given by the area under this green shaded curve. The probability of error when symbol S1 is transmitted is the blue colored area. And these two areas, because of the symmetry of this particular representation, these two areas are identical and they both are equal to this Q of A divided by sigma n. So now, I didn't give you this lab actually, but we can do a laboratory based experiment, basically a simulation based experiment where we can run a simulation of this BPSK symbols every time. So we generate maybe let's say 10,000 bits randomly, ones and zeros. One we encode as plus square root of EB, minus 0 we encoded as minus square root of EB. Those values we transmit over additive Gaussian noise channel with certain variance sigma n, or certain standard deviation sigma n, and we define the SNR as a squared divided by 2 sigma n squared. And that value we vary from 0 to 10 in the simulation. I did that, and the BPSK maximum likelihood rule at the receiver, I implemented that and I measured how many times that BPSK optimal detector made an error. And so as expected, when this SNR or energy per bit divided by the noise variance, as that becomes bigger, it varies from 0 dB to 10 dB, the BPSK demodulator became increasingly more accurate. So at 0 dB, it would make about roughly, but because the underlying concepts are the same, the theoretical answer and the simulation match with each other so well, so precisely. That shows that our program is correct and our analysis is correct, and they both kind of corroborate each other. Okay, so now let us look at one another observation that comes out of this theory, which is that there are only a few things that matter, and those are the things that we should be very careful in designing a classical communication, classical digital communication system. So to understand these two different aspects that are kind of implicit in what we have studied so far, I will ask you to consider three different schemes: scheme 1, scheme 2, and scheme 3. The blue colored circle corresponds to the symbol that gets transmitted when x equal to 1. The yellow corresponds to the symbol that gets transmitted when x equal to 0. And the x-axis corresponds to the transmission voltage. The decision boundary for any of this scheme is always halfway between the constellation points. Why is this the case? I think we already talked about it. This happens because of the symmetry of the conditional probability density functions. Uh, you see these two functions that we have here? They always intersect at the point which is exactly in the middle of the two transmitted symbols, no matter what these two symbols are. Because of the symmetry, our decision boundary, as I have drawn here in the red vertical line, always is halfway between the constellation points. So I hope that part is clear to all of you. The other observation is that the, the theoretical probability of error, and that, as we saw on the previous slide, would also match with the simulation result if we did simulate any of these three schemes. Given a particular value of sigma n, meaning given a certain noise power, the probability of error, meaning how accurate our digital communication system is, it depends only on the distance between the constellation point, and it doesn't depend on the exact amplitude. Can somebody tell me why that would be the case? To explain why the error depends only on the distance between the constellation point and not on their exact amplitude, still the decision boundary is always halfway between S0 and S1, meaning this decision boundary, although it is shown here as 0, it assumes that S0 is negative of S1. In general case, instead of 0, it should be S0 plus S1 divided by 2. That will be the average of S0 and S1. So decision boundary will be exactly halfway. And secondly, given a particular noise density, which is this bell-shaped curve, the probability of error, which is basically the green and the blue curves, the area of those green shaded curve and blue shaded curve, you see it depends only on the distance between S0 and S1, not their absolute magnitudes. For the same noise power, for the same value of sigma n, meaning that this width of this bell-shaped Gaussian density, if I keep them same, and if I bring S0 and S1 closer to each other, then obviously the green and the blue areas are going to increase, meaning that the probability of error is going to increase. On the other hand, if I bring them apart, then they'll shrink, meaning that probability of error will shrink. See, I didn't say that I'm changing the absolute values of S0 and S1. In either case, I'm just changing the distance between S0 and S1. And right away, I'm able to see that it has a direct translation to the performance of the receiver, how accurate it is. So based on that, I can say that the performance of the optimal maximum likelihood receiver depends only on the distance between the constellation points, not on their exact amplitude. Test it mathematically. Remember here I said that, or we derived this actually last time, that the performance in terms of how many errors the receiver makes on average is given by Q of A divided by sigma n. But for BPSK, the distance between the two constellation points is 2 times A, right? One is at plus A, another one is at minus A. And so to generalize, I will say that this error performance is Q function of D divided by 2 sigma n. Instead of A, I will just call it D divided by 2, where D is the distance. D is equal to 2A for BPSK and D is equal to A for on-off key. And in mathematical literature, in the communication textbook, sometimes sigma n is represented as n naught by 2. Sigma n squared is represented as n naught by 2. So sigma n is square root of n naught by 2. So once I make that substitution, the answer that I get is q function of d divided by square root of 2n naught. I don't think we'll have time to explain this, but n naught is called the power spectral density of whitened version of Gaussian noise. So when the Gaussian noise is spectrally white, you take its power spectral density and it is flat, then the height of that power spectral density is represented as n naught. Anyways, so these two symbols at +1 and -1, corresponding energy per symbol are just 1. If I average, 1 plus 1 is 2, but there are two symbols, so the average becomes 1 also. Right? So scheme 3, we can right away say that the average energy per symbol is 1. What will be the energy per symbol for scheme 2? The average energy per symbol? Who can tell me that? Remember, the energy per any transmitted symbol is simply the square of the corresponding voltage. So for scheme 2, the blue colored symbol has an energy of 36. The yellow one has an energy of 16. And so the average energy per symbol that I require for scheme 2 is 36 plus 16, which is 52, divided by 2, which is 26. So you see that in scheme 2, I am spending 26 times more energy. But what do I get in return? Nothing to show off, nothing to write home about. The probability of error is identical to scheme 3 probability of error. So we should not do scheme 2 at all. Scheme 2 is wasteful. It achieves the same probability as scheme 3, but scheme 3 is far more energy efficient. In fact, there is a factor of 26 improvement compared to scheme 2. Now, what about scheme 3 versus scheme 1? Well, what is the average energy per symbol for scheme 1? It is 4 plus 9, so 6.5.
26.
Yes?
Somebody has posted 26.
Yeah, 26 is for scheme 2, correct. But for scheme 1, the average energy per symbol is 6.5. So scheme 1 and scheme 3 are not directly comparable. Scheme 1 gives you better probability of error, but it requires 6.5 times more energy per scheme 3. So obviously, if you are spending more energy, then you expect the corresponding scheme to perform equally better. And so that is what is happening. But is scheme 1 really the best thing, best optimal scheme that one can design? And the answer is no, because I'll just consider another scheme. I'll call it scheme 4, where the distance between the two symbols is same as scheme 1. For scheme 1, the distance between the two symbols is 5. What if I make scheme 4 where the two symbols are at 2.5 and minus 2.5? So the decision boundary, the one in the red, is again centered at 0. So what is the average energy per symbol for this scheme 4? It's going to be 6.25 square of 2.5. The distance has remained the same as scheme 1. So the performance will be same as performance of scheme 1. But the scheme 4 is able to achieve the same for performance by using average energy per symbol of 6.25, whereas we just now saw that scheme 1 requires an average energy of 6.5. So we can say that scheme 1 is also not optimal. It is turning out, based on these examples, that the scheme which is optimal is the one for which this decision boundary is centered at 0. Scheme 2 is not optimal compared to scheme 3 because its decision boundary is not at 0, whereas scheme 3's decision boundary is at 0. Scheme 1 is less optimal compared to this scheme 4, plus 2.5 minus 2.5, for the same reason. But when the decision boundary is at 0, we are talking about BPSK, right? So that is why BPSK, binary phase shift keying, is considered as the optimal modulation. UPSK allows me to take 2 bits of input at a time. And depending on with this, what these 2 bits are, 1, 1, 1, 0, 0, 1, or 0, 0, I will either transmit this constellation point, or this, or this, or this. That is this bits to symbol mapping for QPSK. Okay. Now, when I transmit those symbols, just like what we saw for BPSK, the introduction of noise will create a little bit of spreading apart of these transmitted symbols by the time they reach the receiver. And this is the diagram that we get. What is wrong with this diagram? Can anybody tell me? It seems like this is the generalization of the BPSK diagram that we had seen earlier. Remember this one here? This diagram or this diagram? BPSK is the real part of a complex number. QPSK uses both real and imaginary. So why can't I draw the constellation diagram at the receiver by just direct extension of the BPSK constellation diagram? What is the difficulty with this type of representation? Now, Professor Rajendra, if there are any responses, kindly please let me know.
Error. So somebody is saying error.
Regions. So what it amounts to is that for this scheme, the perpendicular bisectors are basically x and y axis. And so this quadrants, the first quadrant is the decision region for symbol 1, second quadrant is the decision region for symbol 2, so on and so forth. And that is what is being shown here. The decision regions are simply quadrants. All the green colored received symbols get mapped to this particular transmitted symbol. All the purple symbols get mapped to or get demodulated as this symbol, so on and so forth. If you phase rotate the transmitted symbols, then you have to also phase rotate the decision boundaries by the same amount. And therefore, you can see that the decision region for this scheme in the bottom is 45-degree rotated version of the decision region for this scheme. The same type of concept we can apply for another scheme which is called binary frequency shift keying. So we have seen on-off keying, binary phase shift keying, and then we saw quadrature phase shift keying QPSK, and then this is yet another modulation scheme, BFSK, where we use two different frequencies to transmit different bits, ones and zeros. And because we are using two different frequencies, uh, it's sort of like QPSK, but we don't use the negative values. So we still use a complex number, but these complex numbers are just used in the positive sense. The decision boundary is still half perpendicular bisector of the line connecting these two symbols, and so that is this red colored line. QPSK is quadrature phase modulation. We can generalize to M-array PSK. Basically, this is a diagram of 8 PSK. It allows us to transmit 3 bits whenever we transmit a symbol because there are 8 symbols. And the constellation points are 45 degrees apart on a complex number plane. And again, the decision regions are perpendicular bisectors. And so if I transmit, for example, if I transmit this symbol, then any received constellation which falls under the shaded area gets demodulated as this particular symbol, symbol 2, so on and so forth. We are basically cutting slices of a pizza for MRE PSK. And that, I think, is the last observation that I will make before I conclude this topic. I can generalize from QPSK, I can go to 8 PSK, and so far I have just used the phase as the way to differentiate between transmitted symbols. I can also use amplitude in addition to phase. So I transmit these different symbols not only on different phase values, but also on different amplitude values, meaning the radius of the circles on which these symbols are located, I modulate that as well. And then I get what is known as 16-ary amplitude shift keying, or in general 16-ary quadrature amplitude modulation. And why to stop at 16? I can even go to 64 quadrature amplitude modulation. And so when I use 64 symbols, I can actually send 6 bits whenever I send a particular symbol of 64 QAM. I'll skip over this analysis, but for 16 QAM, the decision boundaries look like this. They are always perpendicular bisectors following the maximum likelihood Bayesian detection. And if, for example, this symbol is transmitted, all the received symbols which fall under this shaded region get demodulated as this blue colored symbol in the middle. Okay, so this is where I will conclude this topic on digital communication. There are many other details which are in this presentation. You can look at them on your own, and if you have any questions, you can send me an email later on. But this is where I will conclude this particular topic. And then the last topic for today is the design of non-coherent digital modulation receiver, and that we will take up. Professor Mitrawal, can we take some short break now?
Sure, we can take 5 minutes break.
Okay, fine. So I will start that presentation in 5 minutes.
Thank you.
Okay, shall we begin? Uh,
Your voice is little bit low.
okay, how about now?
Yeah, better.
Okay. So I will start the lecture on the last topic, uh, which is on the design of coherent and non-coherent digital detection methods. Share my screen. Okay, I hope that you are able to see my screen.
Yes, we are able to see it.
Okay. Okay, so uh, I my understanding is that uh, you are studying this topic of classical communication theory so that you are better able to appreciate uh, the nuances and also the concepts of the quantum communication theory. And uh, you can kind of create a contrast between the two once you have this basic mathematical foundation in the classical sense. Then you can generalize to how these concepts get modified in the context of quantum transmission of information. Uh, and possibly the topic or the concept that resides at the heart of classical communication theory is this Bayesian detection rule that I have been stressing about repeatedly. And so that is going to be the focus in this presentation. So we are going to again review the biases rule and how it leads to map and ML decision scheme. And then we will see that as this rule leads to the coherent detection methods, how that can generalize to non-coherent demodulation. And we'll see what non-coherent demodulation is, why it is called non-coherent, and what is the motivation for that. And then maybe we'll take a look at two different examples, non-coherent phase shift keying and non-coherent frequency shift keying. Okay, so that is the general outline of this lecture over next 45 minutes. So we have seen that the Bayesian rule basically, upon getting a particular measurement, for example, y is equal to 1 in case of a binary output of a noisy channel, tries to evaluate the relative likelihood, or sometimes they are also called odds, of x equal to 1 versus x equal to 0. And whichever comes out to be greater than 1, if the odds of x being 1 are greater than uh, for x equal to 0, then we say that x equal to 1 is more likely. The posterior of x given y equal to 1 is greater than posterior of x equal to 0 given y equal to 1. And then we decide in favor of x equal to 1. According to the Bayesian theorem, this ratio of posteriors is equal to the ratio of the product of the likelihood and the prior. Okay, so that is this just comes out of the Bayesian rule. There is also a term which is called probability of evidence, but that term is common for both x equal to 1 and x equal to 0, so it cancels out in this ratio. And additionally, as we talked about just in the previous lecture, when the priors are equal, meaning x equal to 1 and x equal to 0 occur with equal probability, then we just get to be this posterior ratio becomes same as the ratio of likelihood, and this is the one that we evaluated to determine the decision regions for BPSK scheme. And in this case, we saw that decision regions are identical to minimum distance detection. The map decision rule, the maximum a posteriori rule, does not make this assumption. So it allows probability of x equal to 1 to be different from probability of x equal to 0. And so the uh, generalized version of ML is the map rule, maximum a posteriori rule, where we actually evaluate the entire ratio of posteriors. Okay. We saw in the previous lecture that uh, if it is BPSK, then we transmit one of two messages, capital M is equal to 2. If it is QPSK, then M becomes 4. If it is 8PSK, M becomes 8. If it is 16 QAM, M becomes 16. If it is 64 QAM, M becomes 64. So M is one variable that changes depending on which modulation schemes that we are using. The other entity that changes is this capital K. For BPSK, we just needed one dimension, the real valued axis. But for QPSK, 8PSK, 16 QAM, 64 QAM, etc., capital K became 2. The symbols are mapped to a two-dimensional vector. Okay, so that is the generalized mathematical notation that uh, is useful to consider as we move along. And then once we consider the transmitted symbols as basically k-dimensional vectors, then the conditional distribution of R given individual transmitted vector becomes this multidimensional Gaussian PDF, which has this type of mathematical notation. Basically, the output of this multidimensional PDF is still a scalar. It still gives us probability density function, which is a scalar output. And that scalar output again depends on the squared norm between R and S of M. S of M is the transmitted constellation point. And that squared norm gets scaled by n naught or 1 over n naught. Negative of that becomes part of an exponential function. And then there is another scaling that is shown here outside of the exponential function. Now remember, the maximum a posteriori rule is the one which says that we will evaluate the conditional probability of individual S of M, individual constellation symbols, given a particular received vector R. And we will select that symbol to be the one most likely to have been transmitted, for which this posterior is the highest of all. That is the maximum a posteriori rule. And so when we formulate that mathematically, what it amounts to is that we select the argument of the maximum over 1 to m of this quantity, alpha times p of m times p of r given s of m. Remember, p of m is the prior, p of r given s of m is the likelihood of r given s of m, and alpha is 1 divided by the probability of r, which is the evidence. Okay. Now, we have seen that the common terms don't matter. So alpha, first of all, automatically cancels out. Secondly, it's good to sometimes get rid of this exponential function, which we can do by taking logarithms. And so we can also write this map rule in the manner which is shown at the bottom of this slide. And it simplifies to basically this expression at the very bottom. Exponential function disappears in this representation. Now, additionally, if I assume that p of m are all the same, so log base of logarithm of pm are all the same, then when I do the evaluation of which one of them is the maximum, Even this first term disappears, and so maximum likelihood rule simply takes the argument of maximum of squared norm of R minus Sm. Remember, R is a vector, S of m is a vector. We are taking the difference, which is also a vector. We are evaluating its squared norm, basically the squared length of the vector, scaling it by 1 over n naught and applying minus sign. Again, n naught is the common term, we can get rid of it. So this is all this remains. And arg max of negative of r minus sm norm squared is same as arg min of r minus sm whole squared. Okay, but r minus sm is this error vector e of m that we had represented in the previous lecture. So maximum likelihood rule says that you basically select that symbol for which the length of the error vector is the smallest. Okay, now we can even further simplify it. What is the squared length of EM? It is obviously this vector dot product EM Hermitian transpose EM, but EM is R minus SM, so this is that R minus SM Hermitian transpose R minus SM. I can further expand it, becomes this term expression in the third line of this equation. Again, because we are just interested in identifying which n is the most likely value of symbol index, we can ignore any term which is independent of m. So R Hermitian R goes away, and we are left with just these two remaining terms. How to interpret them? R Hermitian Sm and Sm Hermitian Sm. Can anybody say what they mean physically, intuitively? How do you interpret R Hermitian Sm? And how do you interpret Sm Hermitian Sm? Basically, the inner product of Sm with itself and inner product of the vector R with Sm. Any idea? In the interest of time, I will give the answer myself. I think it is always better uh, if, if some of you provide this answer. But let me just move along and say that R Hermitian Sn is the projection of the received vector R onto the signal vector Sn. Right? Inner product can be thought of as a projection operation. Transmitted symbol is this vector S of m. Received vector is S of m perturbed by a noise vector. Then R Hermitian Sm measures basically how close R remains to this Sm. If the noise is not too large, then hopefully this projection will be large. And it will be especially larger compared to some different S of m. And then Sm Hermitian Sm is basically the squared length of this vector S of m, which we have equated to being the energy of that transmitted symbol. And so this ML rule, one way to interpret it is to say that it selects that value of symbol index which minimizes the squared length of the error vector. But other way to say this is that it maximizes the projection of R over Sm. Whichever Sm has this projection being the largest, is the one that gets selected after we subtract half of the symbol energy. If all of the symbol energies are also the same, which is the case for uh, phase shifting, then even E of m divided by 2 doesn't matter, and all we do is just maximize the projection of R onto Sm. Obviously, if the symbols are not equally likely, then we have to also have this additional term, n naught times log base of Pm. And when the symbols are not likely, then the decision boundaries cease to be perpendicular bisectors of the line connecting the symbol constellation points. The decision regions expand for those symbols that are more likely, and they shrink for those symbols that are less likely in a general case. Okay, so I will skip over some of this mathematics and just go to this final summary representation for the maximum likelihood detection, its different formulations, and the design approaches. Okay. Now, one key observation here is that before I can do either this demodulation according to this first line, where I need to measure R minus Sn, or even demodulation according to the last line, where I need to project R onto Sn, what I will need is what is known as coherent receiver. What is coherent receiver? It is a receiver which is in coherence with the transmitter. What do I mean by that? The receiver should be using the same symbol timing, same frequency of transmission, and same phase offset that the transmission is using. In the realistic scenarios, what the receiver is using will have some offsets in terms of symbol timing, in terms of frequency of transmission, and in terms of phase between the receiver and the transmitter. And a coherent receiver is the one which gets rid of those offsets. There is a whole design topic. In a way, it is actually a separate course by itself. How to design a digital communication system which has this time, frequency, and phase coherence between the transmitter and the receiver. It's an entirely it's an entire subject by itself. Just like there are textbooks on digital communication theory, there are textbooks on coherent digital communication systems, where the focus is on the designs that maintain this time, frequency, phase coherence. In my personal experience, I would say that in the commercial systems, for example, if you take any cell phone, or if you take your Wi-Fi modem, or if you take your digital TV receiver, etc., or if you take satellite phones, or even if you take any two computers connected by internet, by Ethernet, etc., wherever there is a transmission of information by means of this digital modulation schemes that we have been discussing, if the system designers, if the engineers require a coherent system so that they can use this maximum likelihood or maximum a posteriori detection schemes, then apart from the design which deals with this equations, which is a design in itself, a significant chunk of the design is focused on achieving this phase coherence. And that we are not at all talking about. How to achieve this phase coherence or frequency coherence or timing coherence is a whole new design engineering topic which we are not including here at all. But in the actual systems, in the operational systems that I just mentioned, I would say more than half, or sometimes more than even 3/4 of the engineering focus gets diverted to these coherent uh, schemes. Okay, so basically all I'm saying is that the engineer who commits himself or herself to building a coherent communication system which can directly implement these Bayesian rules that I have summarized here on this slide will have to devote a significant attention. They will have to solve many challenges that relate to how to achieve that coherence. Because the transmitter is sending some symbols at its own timing, the receiver has no clue what the transmitter symbol timing is. So how does the receiver figure out that timing? Or the transmitter is using some oscillator to transmit the symbols at certain radio frequency. The receiver has its own oscillator, but that oscillator is not frequency locked to the transmitter oscillator. If these two transmitter and receiver oscillators are not in frequency lock with each other, meaning they are not frequency coherent, then all bets are off. You can't do any of this anymore. So how to maintain the frequency lock at the receiver with respect to the transmitter oscillator? Similarly, suppose somehow you are able to get timing coherence and frequency coherence, but if your phase is all incoherent, meaning that the receiver uh, has a phase offset which is not the same that the transmitter introduces, then again all bets are off. Remember for BPSK, QPSK, Emery PSK, 8 PSK, etc., or 16 QAM, we saw those decision boundaries that the receiver makes. Those decision boundaries actually come out of these equations. Well, those decision boundaries are accurate only once the receiver is in phase coherence with the transmitter. Otherwise, if there is a phase rotation between the transmitted symbols and the received symbols, then even if the noise is zero, which is an ideal scenario, the receiver won't work because its decision regions are completely messed up compared to what the actual offset should be given what the transmitter is sending in terms of modulated symbols. And so there are designs called phase lock loops, PLL, and there are designs called frequency lock loops, FLL, and delay lock loops, DLL. Delay loop, loop delay lock loops are for timing, frequency lock loop, FLL is for frequency, PLL is for phase coherence. And there are other schemes as well. But you see that it requires taking up uh, an engineering challenge by itself. And that is the motivation for not doing any of that. Basically, not insisting that my receiver is phase coherent or maybe even frequency coherent. Timing coherence is still needed, by the way, but at least these non-coherent techniques try to not require the phase coherence and frequency coherence. Right? That is what I have written here, that the phase has to be known for a coherent demodulator, and the phase rotates very fast. And so even a small error somewhere in the transmission chain can introduce unacceptably large error in the phase. Similarly, frequency should be known, timing should be known. And all of these parameters, phase, frequency, timing, get perturbed by multipath fading, Doppler effect, imprecision of the local oscillators, unknown delays, etc., so on and so forth. And this is especially the phase part and the frequency part is absolute necessity for coherent demodulation of PSK and QAM because the transmitted information resides in the phase. For QPSK, the way we are transmitting information is by modulating the phase, 0, 90 degree, 180 degree versus 270 degree. For 8 array PSK that we saw, the phase was modulated in steps of 45 degrees. So how to not require phase coherence, let us say. When the channel introduces phase distortion, it may not be possible to remove the effect entirely, but what this non-coherent demodulation schemes assume is that whichever the phase offset is between the transmitter and the receiver, let us assume that it doesn't change from one symbol to the next. So this is called uh, a static assumption. There is some unknown phase offset, but it changes comparatively much slower compared to the rate of symbol transmission. And so under that assumption, when we say that we are transmitting a particular symbol, a modulated symbol was the nth modulated symbol, n is the symbol index. A of n is the amplitude of the symbol, theta of n is the phase of the symbol, and phi of n is this offset between the transmitter phase and the receiver phase. It's a distortion that somehow we need to get rid of. And U of n is the additive Gaussian noise component. With this type of transmission model, if we additionally assume that the phase doesn't change, and also let us ignore A of n, which is a valid assumption if it is an Emery PSK scheme. But even if it is not PSK, if it is QAM, it is okay to ignore A of n for the time being because we are just looking at how to achieve phase coherence. The amplitude component does not give us any conceptual clarity. So we can currently just assume that A of n is the constant given by square root of the energy per symbol. Then this S of n representation simplifies to the one which is at the bottom of this slide. There are two phase terms. One is theta of n, which is the desired phase that the transmitter introduces. Right? For QPSK, it is 0 degree, 90 degree, 180 degree, 270 degree, so on and so forth. For 8 PSK, it is 2 pi over 8, multiples of 2 pi over 8. For 16 PSK, it will be multiples of 2 pi over 16. So theta of n is the intended phase or desired phase, and phi of n is the undesired channel induced distortion that we somehow need to get rid of. And the way the non-coherent schemes work is instead of transmitting S of n, what they do is they transmit the product of S of n and S conjugate of n minus 1. Okay, so that is the main idea. So given that S of n is this term here, square root of Es times exponent of j theta n plus phi, and I got rid of index n with phi because I'm assuming that phi is relatively static compared to theta of n. Then if I do S of n times S conjugate of n minus 1, that is just simple math. Once I go through the math, I get this term at the very bottom of the slide. The first part is the signal term, where instead of theta of n, I get theta of n minus theta of n minus 1. The second part comes from the noise. It's a cross multiplication of noise and the signal. And the last part is just product of the current noise and the previous noise sample, and nth and n minus 1th samples of noise. So now let us denote this individual terms u of n multiplied by this exponential terms as some noise signals wn and wn minus 1. Then this q of n, which is product of s of n as conjugate of n minus 1, simplifies to this expression here at the in the second line of this equation. One more simplification we will do is we will ignore u of n times u conjugate of n minus 1. Although this is an approximation, it is okay sometimes, especially when the noise energy is small. So suppose the noise energy is 1% of the symbol energy. Then when I multiply two such noise samples, their relative energy with respect to symbol will become 0.01%. Instead of percent, it will reduce by a factor of 100. And basically, at that point, we can just ignore it, okay, for mathematical simplification. And so then this product becomes the one that is given here. Now, what we are going to do is we will again get rid of the additional square root of ES component, simplify further, and so we get the expression which is in the middle of the slide. Assuming that Wn and W conjugate of n minus 1, they are independent and identically distributed samples, I can club them into just one noise sample V of n. The only thing is that the variance of V of n will be twice the variance of this individual Wn. That is the property of adding two independent variables. If two random variables are independent, if I add them, their variances add also. Okay, so now this V of n is going to have twice the variance. And so, the V of n, I will still normalize it, but then the fact that it has twice the variance, I will denote it by applying this square root of 2 multiplier. So once I do all the normalization and simplification, what I get is that the receiver symbol is given as square root of Es divided by 2 e to the power j delta theta n plus V of n. Now, as an engineer, we just look at this final simplified expression and see what we have done. First of all, here in this expression, that unknown phase term phi of n or phi is gone. It's got cancelled out, which means that at the receiver we don't have to worry about maintaining any phase coherence at all. No matter what phase offset or phase distortion the channel introduces between the receiver and the transmitter, assuming that that phase offset remains constant from one symbol to the next, this works very well. So we got rid of the phase distortion or the term that required the phase coherent design. But the price that we paid is that the energy per symbol became half. Okay, and then the third thing is that our information now better reside in this delta theta of n, not individual theta of n and theta of n minus 1. So That is the summary of differential phase shift keying. The information resides in delta theta of n. So the incoming bits don't determine the absolute value of phase that the modulator uses, but they determine the difference of the current phase with respect to the prior phase. So if I contrast it with the coherent BPSK, if I contrast coherent BPSK with non-coherent BPSK, what is going on is if nth incoming bit is 0, then theta of n is 0. If nth incoming bit is 1, then theta of n becomes 180 degrees. So 1 and minus 1, or a and minus a, as we saw in the previous lecture. On the other hand, for the differential or non-coherent BPSK, the absolute phase doesn't matter. It can be any value. It can be 45 degrees, 37 degrees, doesn't matter. But whenever the incoming bit is 0, what we do is we don't change that carrier phase at all. We let it continue. On the other hand, if the incoming bit is 1, we take the phase of the carrier waveform corresponding to the previous symbol and we shift it by pi, or 180 degrees. So you see that we are always modulating the differential phases. And so at the coherent, again, that was the transmitter side design. At the receiver side, because coherent schemes explicitly try to compensate for phase, when it gets this R of n, which is square root of energy times exponent of j theta n plus the phase, it has to somehow estimate the phase, get rid of it, and then apply the maximum likelihood or maximum a posteriori rule. On the other hand, for the non-coherent demodulation, that phase term is compensated out because we take the product of the nth received symbol and n minus 1th received symbol, complex, put r sign on top of r n minus 1. But once I do that, that constant phi term gets cancelled out. I just get this quantity, and then I just demodulate it in the standard manner. So the receiver becomes simpler. I don't need to implement phase lock loop at all. But the price that I pay is that, remember we said that energy per symbol becomes half of what it is for coherent BPSK. And therefore, that Q of square root of ES divided by square root of 2 times ES divided by N naught, if that ES becomes half, basically Q function starts giving larger numbers as the answer, which is what we see here. The blue is the coherent BPSK, and the yellow is the non-coherent BPSK. And you can see that there is about 3 dB penalty. Basically, we lose 3 dB, a factor of 2 in the linear scale, 3 dB in the logarithmic scale between coherent and non-coherent schemes. Okay, so and by the way, what we did for BPSK, we can extend it to QPSK or 8PSK, etc. Basically, we again encode the incoming information not in the absolute phase, but in the differential phase at the transmitter. Okay, so that is the same idea that that applies. Okay, it's 3:55. There is one more topic on non-coherent reception of binary FSK, but I don't think I'll be able to finish it within 5 minutes. There is quite a bit of math here. So, Professor Rajender, I'll conclude here and give some 5 minutes for questions and question and answer.
Sure. So, the floor is open for question and answer sessions. If participants have any questions, you may post on the chat. All right, so probably there are no questions. In that case, I would like to thank Professor Yashwa Savda for taking these 7 sessions on the fundamental of digital communication. And I hope participants have enjoyed these interactive sessions. And there is one comment which I can read out. So basically, probably they have enjoyed these sessions, these interactive sessions, and thank you for answering all the queries of the participants during the sessions. And thank you once again for accepting our invite as an expert speaker in this FDP. There are a few questions. Probably we can take those questions and then end your talk here. So there is something we are unable to go into the details of the different modulation, how the question for the test will look like. It's more of related to test. So basically, we'll be posting questions related to what has been covered in the FDP and not the ones, you can exclude the topics which are not covered for the quiz. You can just exclude them. So somebody is saying informative lectures. It's a comment for you.
Okay, thank you.
Lectures are very detailed and informative. Thanks, Yash sir. So that's another comment.
Okay, thank you for the comments, feedback. So I think, yeah, so maybe given the limited time, we could not address all the different modulation schemes and the details of how the coherent versus non-coherent modulation schemes work. But the main central message that I wish to convey is that if you focus on the Bayesian theorem, then from there itself you are able to understand a lot of coherent modulation schemes. The non-coherent modulation schemes basically just try to encode the information in the differential content that you are transmitting. Those are the large high-level concepts. The detailed concepts are in my slides, and yeah, I think you can examine them at your personal uh, in your personal time. And in case if you have any questions regarding these slides, that I think Professor Mithrwal will post to all of you. You can.
I have already posted on Canvas, so the slides are there, and also people have been asking for the links related to the YouTube videos. It's already posted on Canvas. You can see the playlist through the Canvas and also the notes through the Canvas.
Yeah, and in case if you have any questions regarding any of the content in my slides, you can approach me over email.
Yes, so you can directly write him an email if you have any questions related to the slides. He'll be very happy to answer them.
Yes.
I can post the email in the Canvas itself if somebody, otherwise, if you search his name in Google, you'll find his web page and you can find the email there. Anyways, I'll post them on the Canvas.
Okay.
All
Thank
right.
you.
Thank you.
Yeah.
Thank you, Professor Sada.
Thank you, everybody, and thank you, Professor Rajendra Mithrwal. Thanks for inviting me, and yeah, thanks a lot.
See you again in future FAPs.
Sure.
Bye.
Thank you. Bye.